Our aim is to design, build and test a simple wing structure for a small aircraft optimized for minimum mass under spanwise bending and torsional constraints, while outlining the design process clearly and effectively. This process will include 4 phases: conceptual design, preliminary design, detailed design, and acceptance. We started off by looking at the geometry and wing specification data. This allowed us to obtain some basic dimensions to get us started, like the length of the spar being 0.74 meters. From here we did some basic research, where we looked into what shapes generally perform the best in torsion or in bending. Circular beams are strong in torsion but weak in bending, and I-beams are strong in bending but weak in torsion. Box beams have a good balance between both I and circular beams, so we decided to go with a design close to a box shape. Next, we started experimenting with Excel modeling, which allowed us to quickly investigate and develop our ideas. To optimize the dimensions of the wing spar for bending, we employed the Euler-Bernoulli beam theory. Rearranging the equation yielded the stress as a function where the maximum stress was inversely proportional to the second moment of area. Similarly, to ensure the spar was compliant in torsion, we used torsional compliance equation, where the maximum twist was inversely proportional to the polar moment area of the spar. Additionally, the equation for deflection of the tip was dependent on an equation which was again inversely proportional to the second moment of area. As many of the variables in the equation were determined by the specification already, this meant that the compliance of our spar depended largely on the geometry of the beam. By inputting the new equations for deflection, torsion, and maximum shear in terms of the width, height, and thickness of the spar, we could find the theoretically optimal configuration that minimized all 3 functions. This meant that having thicker sections on the top and bottom of the neutral axis decreased the direct stress in the spar, giving us 2 ideas: one slight rectangular spar with thicker top and bottom pieces, and one spar with an X going through the beam and a separate structure. It's also very important to leave enough material thickness between the edge and the ribs of the spar. Therefore, although a larger cross-sectional area for the spar may be more optimal for torsional compliance and direct stress, a smaller spar will make sure we do not compromise the integrity of the ribs when using the laser cutter, and so we will need to have a stronger internal structure that can reduce the direct stress while keeping the cross-sectional area within our limit. The use of SolidWorks allows us to simulate and experiment with more detailed and complex designs to help us meet our goals. The static SolidWorks simulations come with a few assumptions, such as linearity, elasticity, and static assumptions. We modeled and placed our designs into SolidWorks, then built the rest of the structure around it. After conducting a bending static simulation of the spar, we found that the stress was highest right next to the mounting point, and was weakest on the horizontal walls next to the neutral axis of the spar. This is also shown in real-life testing where the spar buckled or tore at those exact spots. This meant that the beam didn't need to be equally thick along the whole cross-section, only nearer the mounting point. After a torsional test was conducted, we also found that the parts closest to the neutral axis experienced the most stress in torsion. This meant that we couldn't remove too much mass from the sides as torsional strength would drop dramatically. We tested a few different methods of decreasing thickness along the beam, and found that the best solution was using 2 extra slices of foam rod on the top and bottom of the spar that got thinner along the spar, which saved a significant amount of mass. We also decided to optimize the strength-to-weight ratio of the ribs. To do this, we started by just cutting holes out. However, this didn't seem to be an optimal solution, so we used the topology study feature in SolidWorks that located the areas that mass could be safely removed without compromising the strength of the rib meaningfully. Finally, after a few iterations, we discarded the cross design and stuck with this for our final design. Moving on to our last phase, we built and tested our final design against our initial goals and evaluated the design's positives and negatives. When we tested the spar for bending, we found that it met its displacement requirement at n=1 and passed the bending test at 24.5 newtons or an n value of 2.5. In the torsional load test, the spar rotated about 1.25 degrees per newton meter and so easily passed. In conclusion, the wing met every requirement provided and was optimized for mass. While we feel that the spar could have been optimized further, more time would have been required to perfect it.